All right, so today's class we are looking at topic 6, which is called Above the Atmosphere and Under Control. So Earth's atmosphere, which we talked a little bit about already when we were looking at telescopes, the atmosphere prevents astronomers from getting a clear view of the universe. So to get a clear view, astronomers, they have to place their telescopes into orbit above Earth's atmosphere. And there's two technologies that make that possible, to put telescopes and spacecraft into orbit and keep them there, and that is rockets and computers. So rockets, they were invented hundreds of years ago. They were first used for fireworks and weapons. So a rocket is a tube that contains combustible material in one end and a payload on the other end. The payload refers to the device or material that the rocket carries. So the product of the combustion, the exhaust, it escapes out one end, and the tube is pushed in the other direction by the action-reaction principle. And that payload, it can be an explosive, it can be a measuring device, it can even be a person. Rocket fuel, we'll talk about next. So exhaust velocity, this is the speed at which the exhaust leaves the rocket. It's one factor that determines the rocket's range, which is how high or how far a rocket can travel. So here we see Dr. Robert Goddard, an American physics professor. He was the first scientist to successfully launch a liquid fuel rocket in 1926. He also knew that if a rocket had more than one stage, that's called a staged rocket, it would fly faster and higher. A staged rocket is basically having stages. It's sections of a rocket that will drop off once its fuel is used up. That will make the remaining part of the rocket lighter. All right, so that's him standing next to his first successful liquid fuel rocket. It was over 2 meters tall, and it was made of 2 sections. So next, we'll talk about the V2 rocket, and we'll talk about Wernher von Braun. So he was a German scientist, and during World War II, he experimented with liquid fuel rockets to help the Nazi war effort. The world's first ballistic missile was their V2 rocket. It was launched in 1942. This is a ballistic missile. It's a bomb that is powered by a rocket engine. So the V2 test rocket, it successfully hit a target about 200 kilometers away from the launch site. And almost every rocket that's flown today for military use or for space exploration, it's a variation on this design of this V2 rocket. So near the end of World War II, the Americans captured von Braun and his team of engineers, and they were sent to the United States to continue developing rockets. So this team of scientists then helped launch the US space program. And it was Wernher von Braun's team that built the rockets that took the first US astronauts into space in the 1960s. So when we're talking, you might hear the word cosmonaut when we are in this module. That's the Russian term for astronaut, so a cosmonaut. So after the World War ended, the Allies assembled 3 V2 rockets for test flights. A Russian Army Colonel, Sergei Korolev, he watched these V2 tests in Europe. He later then became the chief designer of the Vostok, Voskhod, and Soyuz rockets. And these rockets launched all of the Soviet cosmonauts into orbit. Right, so here we can see the V2 rocket, the world's first ballistic missile, and then near the end of World War II, Germany launched many of these at Great Britain. And then computers computers were used as well. So the Americans and Russians, they used rockets to launch spacecraft into Earth's orbit in the 1960s, and it was computers that were used to calculate and control their orbits. The first electronic computer, invented during World War II, and was used to decipher coded messages. These first computers that were being used, they were very, very large. So large that their central processors, they filled entire rooms. Eventually, the computers were made small enough to fit inside spacecraft, and these worked with the ground computers to control the flight. So these computers are very important. They're used to calculate orbits. They keep track of other satellites, as well as space junk from other flights, so that satellites don't hit each other in space. These computers, they collect and store and analyze data, and to execute orbital maneuvers of the satellites. All right, so we'll pause here, watch a couple of these. Next, we're going to talk about using gravity. It's something called gravitational assist. This is a method of acceleration. So it enables a spacecraft to gain extra speed by using the gravity of a planet. So what happens is the craft gets sent around one planet. So for example here, and that planet's gravity attracts the craft, causing it to speed up and then change direction. And then that craft can be used like a slingshot, like shown here. It'll slingshot away from the planet at a higher or lower speed than it had before its encounter with the planet. Okay, and that extra speed it gains can be used to send the craft towards another planet. But again, computers and computer programs are needed to calculate the orbit around that first planet in order for this gravitational assist to work properly. All right, so that's what we're seeing here in this diagram. Next, clarifying images. CCDs, these are charge-coupled devices. These are devices that can convert light signals into electric signals in digital format. Those images can then be sent to a computer. Those images are then processed in many ways using computer software. So this is an image from the Hubble telescope. It shows a natural color image of a galaxy. So it was the computer that calculated the colors mathematically. This shows Saturn. It's again an image from Hubble. This is an infrared radiation. Infrared radiation again is using heat. So this here is using colors that represent infrared radiation coming from the planet. This is another Hubble image showing the actual colors of a nebula. They are enhanced though by a computer to bring out the finer detail. So we'll talk about the Hubble Space Telescope. So astronomers, they designed the Hubble Space Telescope, named after the astronomer Edwin Hubble, to get a clearer view of the stars from above Earth's atmosphere. So in April of 1990, the Space Shuttle Discovery blasted off with the Hubble Space Telescope on board. It's the size of a bus, this telescope, a main mirror, 2.4 meters in diameter. And then there are computers on the ground that communicate with onboard computers to direct Hubble's actions. All right, so that was a video on the Hubble Space Telescope. So we're just going to spend some time now on the James Webb Telescope. This here is the NASA website on the James Webb Telescope. So we'll just take some time and take a look at that. And then I do have a short video here on the discoveries using the James Webb Telescope. Just going to pause here. Okay, so moving on, we're going to start talking about what's an artificial satellite compared to a natural satellite. So an artificial satellite, it's a device that is made by humans. So anything like a spacecraft or a telescope. So an example would be like the Hubble Space Telescope. That's an artificial satellite. A naturally occurring satellite would be anything like the moon, the earth, anything naturally occurring. Artificial satellites. Artificial satellites can be used to look down at Earth itself. These types of satellites are used for communications, observation, monitoring, navigation, as well as mapping. They carry instrumentation, so including computers, their own power source. It's usually in the form of solar panels. And we'll take a look when we see the video. So we'll look at communication satellites. So there's two types of orbit. So if we have Earth right here, there is low orbit right here. This is called the low Earth orbit. And then there's another one here called the geosynchronous orbit. All right, so the low Earth orbit we'll talk about here. It's about 200 to 800 kilometers high above the ground, and satellites are placed right here. They complete one orbit of Earth in about 1.5 hours, and they circle Earth faster than Earth rotates, so they move across the sky in like a matter of minutes. They have antennae, we can track signals, and so on. So when we talk about communication satellites, they are placed here in that low Earth orbit. We also have the geosynchronous satellites that are placed in geosynchronous orbit. They move in the same direction as Earth rotates. It's about 36,000 kilometers above Earth, directly over the equator. They take 24 hours to orbit Earth once. So they're synchronized with Earth's rotation. And when we look at them, they appear to be motionless over a point on Earth's surface. And then they have stationary antennae that are used to track satellites. So radio and television satellites are placed in geosynchronous orbit. A problem with having geosynchronous satellites for telephone communications is there's a noticeable time lag during telephone conversations. Therefore, low Earth satellites are used for communications because they will eliminate the lag because they're closer to the ground. So it speeds up the signal transfer between people who are talking. There are many fleets of low Earth satellites. They can establish or accomplish the task of enabling people across the world to communicate with each other. There are also observation and monitoring satellites. They're used for forecasting weather, carrying out research. They help ships, aircraft, and other vehicles determine their exact location on Earth. Okay, so here in this example, satellites can be used to measure depth of snow, extent of ice buildup in Arctic waters, locations of forest fires. Here is a fire. This is an image of a fire or smoke from fires. This is from 1998 in northern Canada. This is showing Landsat, which is a series of satellites that look at Earth at land. That's why it's called Landsat. So these are Landsat images. Let's see the left image, the Chernobyl nuclear power plant. Just after the nuclear accident in 1986. The right image is 6 years later, showing that same area. So the red fields are showing healthy vegetation, and then the darker fields show dying vegetation. Next is remote sensing. This is the science of taking measurements of Earth, as well as other planets, from space. So satellite images, they are computer processed to show, for example, healthy versus unhealthy vegetation. We can see clear-cut and burned forests. Those can be mapped to show the rates of their degradation. Water pollution can be imaged, erosion can be tracked, land use in cities can be observed, weather can also be tracked. So a lot of important uses for remote sensing. Next is GPS. That stands for Global Positioning System. Again, it's a method, or it's a device to which determines your location. It's a technology to find out where you are on Earth. So there's a fleet of GPS satellites above Earth, and small handheld GPS units that are on Earth. So the satellites, they send out radio signals announcing their position and the exact time. And then the handheld GPS unit contains a receiver and a computer. So it can detect radio signals, can measure the distance to each satellite, basically by comparing how long the signals take to receive. All right, then that unit can calculate your location on Earth. It uses the triangulation method, which is programmed into the system. So originally, the US military was using these satellites to provide their forces with around-the-clock navigation and in any kind of weather. And now we see it just on our smartphones and so on. We have GPS programs in there. All right, quick couple of videos here. I'm going to pause here.